Okay, so since we're understanding what the definite integral is and what it looks like, and we got down some concepts like the fundamental theorem of calculus, part 1 and part 2, my aim today mentions antiderivatives, okay? So that's what we're going to discuss. So in your graphing calculator, if you look under math, okay, it actually indicates derivatives and antiderivatives or integration. You have to scroll all the way down though to like 8 or 9. Let me take a photo. So this is what it looks like on mine. If the calculator is allowed on the AP exam, so we've been over how section 1 part B can allow it, and section 2 part A can allow it. You must set up the problem, okay, as if you're going to do it by hand, so show the substitution, what A is, what B is, etc. And then you can find your answer on the calculator. And this is mostly for the free response section, you still have to set up what you're going to do and use, and then you can write the answer from the calculator. They're never going to ask you to put in what is the syntax, okay? So don't write out the steps on how to use the calculator. Don't say use this right here or that. You don't get any credit for it. You have to actually set up the integral, show what you're substituting to get the credit before the answer. So I just want to show you where it is in the calculator. Now you can also do integration in the graphing section of your calculator as well. And this is really nice because it does shade in when you're using integration, the area under the curve, because if it's bounded to the x-axis and positive, it'll show you that. But it'll also show you how, if it's a negative function, it's bounded to the x-axis and what it looks like when it's below the curve. So I'm going to do both, and that way you kind of get to see. So I'm going to erase this slide and show you what I can. So first I'm doing this choice number 9, and let me take a picture of it so you can see what mine looks like. So you can see you're just entering in the information as you see it, 0, 10, and then do the division. Please use parentheses for your numerator and denominator. You actually don't need it for this numerator here, but you do need it for your denominator, because there's more than one term. And then put in your variable. It will be x when you hit the variable key. Keep in mind that your calculator should always be in radians. And when you press enter, it should give you an answer. So let me show you what that looks like. Okay, if you have an older model or you have a different calculator, you need to go through the manual or Google what the manual is and how to enter it. You may have to put the function, you may have to put lower bound, upper bound, and the variables, something to that effect. So please make sure that you do find that information out. So as I said, you can also do this graphically. If you enter in your integrands as y sub 1, and you go to your calculate menu, you're going to notice how 7 is that integration that we have. And what's really great about this, because if your window will show from 0 to 10 for your x values, which a standard window would, then it'll also show you the area under the curve there, okay? So you also may want to know to adjust your window, what your y values are in your table. So you're going to find that they're really, really small. So you may want to adjust accordingly so we get to see what values we actually are using here. And so you'll get a nice graph, but if you actually press number 7, the lower limit is your lower limit of integration, and you hit 0, enter. Your upper limit is your upper limit of integration, 10, enter. And let me show you what it gives you. So it shows you the area that it's finding, and if it's below the x-axis, remember you could end up with like a negative answer, or it's still positive or 0. But this was entirely above, so we get to see the application, we get to see the answers are the same when you integrate. So it's really helpful because it kind of like ties everything we've learned so far together. And you get to check your answers this way also. Now, if you don't have a graphing calculator, obviously you can't depend on using this, but we went over how to do it by hand in other problems and in future problems. Okay, so I have other problems for us, and particularly I'm going to try to do part of this so that we can continue the rest of it tomorrow. In this problem, we not only have a graph, but we have some other information given to us. I'm going to do the best that I can to kind of draw it out for you. So please listen and draw it out into your notebooks as well. I'm trying my best here. So when I'm sketching this out, in my book, I can see that 0, -6 is a point, 3, 0 is a point, and 6, 6 is a point. It describes this as 6, 6. But this was all a straight line segment. You can see that. And then thereafter, it becomes a curve. And they describe this point here as 7, 6.5 or 6.5. So then it comes around to this point here. And they don't describe what that one is, but it does touch the x-axis. So this is f of x. Now they also describe to you more information. F is a differentiable function whose graph is shown. And that the position at time t, which is in seconds, of a particle moving along a coordinate axis, is, and they give you, an equation, s is equal to the integral of f of x dx from 0 to t. All right, so they don't describe if it's along our horizontal axis, which is typically the case in most of these calculus problems, or our vertical axis, but it is along a coordinate axis. Okay, tongue twister there. So now in part A, when it asks what is the particle's velocity at time t is equal to 3, that means that we need to take the derivative of our position. So in A, if we take the derivative, we're taking derivative on the left, okay, which is velocity, and we're taking the derivative on the right. And by taking the derivative over here, we're writing d over dt because these two have to be the same variable. And if you remember, this is FTC part 1, okay? So your velocity becomes just f of t, okay? And also you should remember that this is like the dummy variable. So I can still look at the graph of f to determine the value for the velocity. And so we want it when t is equal to 3. So when t is equal to 3, we're getting an answer of 0. And that is the answer for part A. Okay, so I'm going to run out of space here. I'm going to erase some of the wording of the problem. In the meantime, get down part B. So part B asks for, is the acceleration of the particle at time t equals to 3 positive or negative? So we just need to know what the sign is for acceleration. And this ties in with what we did in part A, because acceleration is the second derivative of position, or the first derivative of velocity. So that is acceleration. And that means that we're taking the derivative of f of t. So this is f prime of t. So now what's happening when t is 3? We're looking at the graph, and if you notice, this is the part where we have that line segment I was discussing. And so we know the slope is kind of given to us. So we can calculate the slope, but we just need to indicate that this is positive. The slope is positive. Okay, and so we kind of answered our question in B. So let's take a look at C. Okay, get down C. So in A, we knew the first derivative, and that implied using FTC part 1. In B, we knew the second derivative, so we just looked at our slope of our tangent line. And in C, okay, it wants to know what the particle's position is at t is equal to 3. So we're going to actually just plug in 3 for t. So this goes out to our old type of problems, okay, where we can use the area under the curve to figure out the integral. So from 0 to 3, we actually have this shape here, and it is a triangle. Now the integral is going to be negative because it's below the x-axis. So 1/2 base times height, we're getting an answer of -9, okay? And that is the particle's position when it at time, t is equal to 3. So let me erase B while we do D, and then I'm just going to call it a day there. We're going to finish the rest of this in our next lesson, but hopefully you can understand how things are kind of connected together. D. So it wants to know when the position is equal to 0, okay, because that's where it passes through the origin, not necessarily when t is 0. So this occurs when t is equal to 6, and here is why. Because we already kind of calculated the area below in part C, and that was -9. If we were to calculate the area above, that would be till when t is 6, then it is +9. This should make sense. When the area below is the same as the area above, its integral is going to be 0. And that's what we want for our position, okay? Because remember, our position was our integral. And that's it. So do some more problems. Let me know if you have questions, and good luck.